Well, hello there, ladies and gentlemen. Welcome. This is Mr. Loos. This is HL Chemistry Flipped Classroom. Today we're going to be talking mainly about bond enthalpy and calculating delta H's from bond enthalpy. We may have done the bond enthalpy POGL in class, which is good, but the purpose of this video is to make sure that we're on the same page and to give a little more help with fully understanding all these concepts around bond enthalpy. So, as often is the case, and especially in this unit, there's a lot of terminology we need to really precisely define and understand the definition of. Average bond enthalpy is the energy needed to break a mole of a particular type of covalent bond when in the gas state under standard conditions. So this is always endothermic. Bond breaking is endothermic, so this is always going to be an endothermic process. As just a for instance here, an equation that would show an example of a bond enthalpy. This is a carbon-carbon single bond being broken. To meet this definition, this would be in the gas. This would need to be in the gas state. There's just another example, and these are in your data booklet, as we'll see later. I mean, you can write down these examples if you like. It's good to know what the equations would look like, but the unit's kilojoules per mole. So literally breaking 6.02 times 10 to the 23rd of these carbon-carbon bonds on average requires 348 kilojoules of energy to do so. And the oxygen-oxygen double bond is 496 kilojoules per mole. So as the definition suggests, this only works for substances in the gas state. And the strength of the covalent bonds varies according to other nearby bonds, so average bond enthalpies are not always completely accurate. So we have talked, or we will talk about several different ways to find delta H's for reactions. Finding delta H's from reactions from bond enthalpies tends to be one of the least accurate ways to do it. But for instance, we've talked probably in this class already about finding delta H's of reactions from heats of formation. That tends to be more accurate because it's more specific. Here, these bonds are only, this data is only based upon an average. It would be sort of like if I assumed what your height was, or if I said what your height was based on the average height of all 17-year-olds or 16-year-olds or however old you are. The average height of a 16-year-old or a 17-year-old might be a pretty good guess for your height, or it might be pretty far off. It's the same here. So, for instance, like look at these two different compounds here. We have CO2 and we have, this would be called propanol, propanone rather. There's a carbon-oxygen double bond in both of these. However, these are not going to be the same strength necessarily, because the other stuff around this bond influences the strength of that bond. So average bond enthalpy is only an average of all the carbon-oxygen double bonds. And that average is not necessarily going to be accurate for either of these compounds in particular. Now we could look up heats of formation, which is going to work better because that's more specific. So let's jump in and look at some examples. Now again, if we've done the bond enthalpy POGL in that particular thing, you've done some examples and some practice with this, but let's just go and make sure we're all on the same page and have an understanding of how to do these things. So suppose you are asked to find the combustion of methane, the delta H for the combustion of methane, using bond enthalpy data. So we have a reaction there that's balanced. Now technically, to be using heats of bond enthalpy data, everything should be in the gas phase here. But the first thing you absolutely need to do is you need to draw the Lewis structure for all of these things. Because if you don't know the true exact Lewis structure of all of these items, you're going to do the bond enthalpy incorrectly. So we have CH4 plus 2O2. Now this is just an example of one of the many areas in which the information in this class builds. We did Lewis structures a couple units back. You still have to know how to draw Lewis structures to do this unit successfully. I can't right now go all the way back through to talk about how to do Lewis structures. If you forgot, maybe you should go back and look at that video. But for the CH4, ends up having the carbon in the center, and it looks like that. As far as the O2, when you actually draw it properly, you will see that O2 has a double bond. So that's one of the reasons. I'm not drawing the non-bonding electrons in these Lewis structures because it's not important in this context, but notice I also drew two of them. I actually drew two O2s because of the two right here. CO2 ends up having two double bonds like that, and then H2O, and again I'm actually going to draw two H2Os. And again, leaving the non-bonding electrons off, you know, like there's supposed to be a couple of pairs of electrons here, but that doesn't matter when you're doing these bond enthalpy things. So once we have this, then we can look up the strength of these bonds. And so to do that, we find in our data booklet table 11, which is the bond enthalpy table. We, for instance, can look up the strength of a carbon-hydrogen bond like so. We can see the strength of a carbon-oxygen double bond like that, and so forth. So we can look up the values of all these things. Now I'm going to go ahead and the carbon-hydrogen rather, single bond is 414, but notice there's 4 carbon-hydrogen single bonds here. So I have to multiply this by 4. This is why you have to know exactly what the Lewis structure looks like. And then I'm going to add into that 2 oxygen-oxygen double bonds, which is 498. And we're going to multiply that by 2. Now, just a quick thing here. These are the bonds, these are reactants, so these are the bonds that I'm breaking, which is endothermic. So these values are positive. There's a few different ways you could do this. You know, a lot of people want a formula. I can tell you a formula you can use in just a second, but I just like to think about it conceptually. I like to think about what bonds am I breaking? Those are going to be endothermic. Those are going to be positive values. And what bonds am I forming? Those are going to be negative. And then once I figure that out, I can just sort of add everything up. So I'm breaking 4 of these. That's endothermic. I'm breaking 2 of these. That's endothermic. Now I'm forming these bonds. That's exothermic. This is going to be, if I look on the sheet here, I see 804, but since it's a bond formation, I got to write it negative 804 times 2, because there's 2 of the carbon-oxygen double bonds there. And in the last step, I have negative 463. And that is the strength of the oxygen-hydrogen bond. Why don't you take a quick second and see if you can decide what I should multiply that number by. So hopefully you said 4 there, because there are 4 oxygen-hydrogen bonds in the 2 H2Os because of the coefficient 2 there. 1, 2, 3, 4. Okay, so then at this point, kind of do all the arithmetic here. 1656 plus 996. The unit's kilojoules per mole in all these, by the way. Negative 1608 plus negative 1852. So I just need to add all this together. This plus this plus this plus this. And we end up getting negative 808 kilojoules per mole. So there we've done it. We've calculated the heat of combustion of methane using bond enthalpy data. Our value is negative, which is good. That makes sense. Combustion's exothermic. We're required to know that. So our answer makes sense from that point of view. Now there's other ways, like we've talked about, that you can find the delta H of this reaction, and how you would find it kind of depends on what the problem said. You know, in IB, a problem will often say, find the heat of combustion using bond enthalpy, or find heat of combustion using heats of formation. So that would be the other way that we could do this. We could use our data booklet again. We could use heats of formation, and instead of using bond enthalpy data, we could use heat of formation data. And that's what we're going to do, products minus reactants. And just as a quick reminder of how this is done, 2 times H2O's heat of formation, so we'd have to look that up. And sum everything together there using the information on this table right here. Remember, oxygen's not going to be in there because elements have 0 heat of formation. That's methane's heat of formation right there, which you can see on the data table. So we get 891.1. So decently far off from the previous answer that we got, which is negative 808. Now this one is the one that is going to be more accurate because this is data that is specific to these compounds, whereas when we're doing bond enthalpy, those are just averages. So I said, some people really like formulas, so I said I'd give you a formula. This formula we should have already talked about. If you're doing the kind of thing that I just did, heats of formation, you do heat of formation of products minus reactants. If you want a formula for bond enthalpy, you have to do reactants minus products. And so, these are the bonds broken here in our reactants. These are the positive ones, and these are the bonds formed. These are going to be the negative ones. So if you use this little formula, you have to do reactants minus products. Or you can just, and that basically this minus sign flips the sign of all the bonds you're supposed to be forming, which is what I did anyway in the example. However you want to do it, whatever gets you there, that's fine. Note that we're going to do this for a lot of different things. So we're going to see almost always we're doing products minus reactants. You just have to remember that bond enthalpy is the one case where you have to do reactants minus products. Now, there is even another way that we could, using our data booklet, find the enthalpy of this reaction. Do you know what it is? Why don't you see if you can figure it out? And the answer is you could just look it up directly in the data booklet. It's in table 13. It's right there. And notice this value is a lot closer to the one that we calculated using heats of formation than it is the one we used for using bond enthalpies. There's a couple of reasons for that. Again, because they're averages. Also because we're forming water as a liquid here, which using bond enthalpies, we should only be forming water as a gas, which does make a bit of a difference. So just an example of how using heats of formation are more accurate. Now, the method that you should use depends on what you're asked to do in the test or what information you have in front of you. If they ask you to find the heat of combustion of methane, there's probably working points for doing it by a certain method. So looking up the heat of combustion directly almost seems like a little magic trick like this one. It's a magic trick for this orangutan here. Which, this orangutan, I think it's, or whatever it is, it's an ape of some kind, gets a big kick out of the little magic trick. I just love his reaction here. But anyway, so all right, now this might seem kind of out of nowhere, and I guess it somewhat is, but in the IB syllabus now, they've sprinkled in some environmental chemistry stuff throughout the syllabus. We're going to probably talk about this more at a later date, but let me just kind of mention it for now. One thing that they want us to do is relate what's going on with the ozone in the upper atmosphere, which helps protect us from ultraviolet radiation from the sun, and kind of relate that to this bond enthalpy concept. So oxygen, regular old O2, has a true double bond, and ozone has a resonance structure, and again, stuff from previous units coming back to haunt us here, very typical for chemistry. So this is a true double bond. This is somewhere between a double bond and a single bond. It's like a 1.5 bond. So this is a stronger bond. This is a little bit weaker of a bond. O2 can absorb high energy ultraviolet light. They call that UVC. So basically a photon of ultraviolet light of a high energy will come in here and it can break this bond. And when it breaks that bond, it basically gets, the photon of light gets destroyed. So therefore, that harmful piece of ultraviolet radiation is not going to come down and cause harm to us. So regular old O2 blocks a bunch of the UVC light that's coming in. And it splits it into highly reactive oxygen atoms, which are called radicals, which go on to create more ozone. And it's a good thing that that happens. But we'll talk more about that at a later date. Now, the thing is, there's also lesser energy light, which is called UVB, and basically that UVB light is not strong enough to break this bond. So basically UVB light will just be kind of passed through and keep going. So ozone is what helps stop the UVB light. UVB light is strong enough to just break this bond in ozone, but not strong enough to break the bond in O2. So then that will split the ozone molecule. And there's a whole system where the ozone gets replenished and all that stuff, which we'll talk about. But basically for now, just kind of know the differences in bond strength between the O2 and the ozone, and the fact that oxygen can block higher energy light than ozone can.